Okay. So let's start today with a KP example, and then we'll do another example, and then we're going to talk about the last K, well, not the last K, but one of the last Ks, which is Ksp. So the example, sulfur dioxide and oxygen were mixed in the molar ratio 2:1. So sulfur dioxide and oxygen were mixed in a 2:1 ratio, and it was converted to sulfur trioxide. Like that. And they were allowed to reach equilibrium at a total pressure of 4.45 atmospheres. At this point, 28% of the sulfur dioxide was converted to sulfur trioxide. Calculate Kp for the reaction.
Are you just balancing on the other side?
Yes. Okay, so it says they were mixed in the molar ratio 2:1. So we're just going to say 2 moles, 1 mole, and we always start with zero product. So far, so good. And then we have our change, minus 2x minus x plus 2x. And then it tells you at this point, 28% of the sulfur dioxide was converted to sulfur dioxide or sulfur trioxide. So 28% of 2 moles was converted to sulfur trioxide. So what's 28% of 2? 0.56? So we lost 0.56. And that's 2x, so plus 2x is 0.56.
You just divide them by 2, right?
Right. So this is 0.28. So 1 minus 0.28 is 0.72. And 2 minus 0.56 is 1.44. And those are mole values at equilibrium.
So once you find like the 0.72 moles and the 0.56, you add together to get 1.4?
Nope, I took 2 minus 0.56 because 28% of it was converted. So this is 72%.
How did you get the 0.72?
Because half of, this is 2x, 0.56 is 2x. So x would be 0.28, and 1 minus 0.28 is 0.72. Okay, so those are mole values, but I'm trying to find Kp, so I need partial pressure values. And I have total pressure, but I need to find partial pressure by doing mole fractions. So to find mole fractions, I add up my total number of moles, which is 2.72, and I divide all of these by that.
Wait, how is it 2.72?
Those three, the total number of moles combined. And I get 0.53, 0.26, and 0.21. Those are like your percentages of moles, mole fractions. Then I multiply those by the total pressure to get my partial pressures. And I get 2.36 atmospheres. And I get my partial pressure values. Then, to calculate Kp, I take my product and I have to square it, divided by my reactants, and this one needs to be squared. And I get 0.134. And that tells me that at equilibrium, this lies to the left. I have more reactant than product at equilibrium.
How'd you get to 2.72?
That was my total number of moles. I added up that plus that plus that. Because I'm doing like a mole fraction or a mole percentage. Questions?
So is this like the stuff that's on like the first worksheet and the second worksheet?
Okay? Let me erase. Ksp. So Ksp is the solubility product constant. So, if you remember, in Chem 1A, probably during quarantine, we learned about solubility and the idea that some things are soluble, meaning they dissolve in water, and some things are insoluble, meaning they do not dissolve in water. And in Chem 1A, it was very cut and dry. It was, yes it is, or no it's not. There was no gray area. Well, now we're finding out in this unit that it's actually a very gray concept. And because of water's special properties, everything is somewhat soluble in water, even if it's just a little bit. So, no matter what we put in water, some of it will dissolve. Even if it's just a very, very small amount, everything is soluble to some extent. And if we write an equation like this one, where we take solid silver chloride, which in Chem 1A we would have said is insoluble, and we put it in water, we get some silver and some chloride ions. And then if we were to calculate a K value for this, Ksp, we would do the concentration of silver ions times the concentration of chloride ions, because you never include a solid in your K equations. And what we're going to find out is the larger the K value, the larger the Ksp value is, the more soluble the thing is, because the more ions you have at equilibrium. So large Ksp values tell us that that thing is what we call extremely soluble in water. If you have a very small K value, like something times 10 to the negative fifth or times 10 to the negative sixth, that's a very small amount of ions, and that's what we call sparingly soluble, just barely soluble in water. But Ksp values give us an idea of how much is it going to dissolve, and therefore how likely is it to precipitate if you mix it with something else. And we're going to get to examples of that later. Okay. Number 1. At a certain temperature, the molar solubility of the salt M2 plus X2 minus is found to be 4.156 times 10 to the negative 6 molar. Calculate the Ksp for the salt. So what it is it's Mx dissolves into M2 plus and X2 minus. And the molar solubility tells us that 4.15 times 10 to the negative 6 moles of that stuff dissolve per liter of water. That's what molar solubility means. So if 4.15 times 10 to the negative 6 moles per liter of this dissolve, your concentration of both of these, it's a 1-to-1 ratio, is 4.15 times 10 to the negative 6. And then to calculate Ksp, you would take 4.15 times 10 to the negative 6 times 4.15 times 10 to the negative 6. And you would get 1.72 times 10 to the negative 11th.
So all you do is you multiply concentrations.
Questions about that? In this next example, you're given the solubility of calcium sulfate to be 0.66 grams per liter. Grams per liter is not a concentration, so we have to convert that to molarity using the molar mass of calcium sulfate. So before we do anything, we would say, okay, 0.66 grams per liter, and it's calcium sulfate. So you would add those up, 40 plus 32 plus 64, 136 grams per mole, and you would get molarity. And then you would treat it exactly the same. And these values are going to tell us, is this thing soluble or not? How soluble is it? In this case, 1.72 times 10 to the negative 11th Ksp value means it does not go very far to the right, which means it does not dissolve very much in water. You don't get very many ions. Things like sodium chloride have huge Ksp values because they do dissolve easily in water and you do get a lot of ions. So that's what our Ksp values are telling us. The bigger they are, the more soluble it is. Here, number 3, given that the Ksp value for silver sulfate is 1.41 times 10 to the negative 5th, calculate the molar solubility of silver sulfate and its solubility in grams per liters. So silver sulfate goes to 2 silver plus and sulfate. So my K equation would be the concentration of silver squared times the concentration of sulfate but really, if we're talking about molar solubility, we're talking that this would be X and this would just be 2X. So it would be 2X squared times X, or 4X cubed, and then you solve for X. That's what molar solubility would be.
And then using that into the molar mass to find the grams.
Mm-hmm.
That doesn't seem too bad.
It's not too bad. Okay, so I'm going to stop there. Tomorrow, the first thing I do in the video is I'm going to go over this number 4 because this is confusing and I feel like the kids who are at home need to see me work this. So make sure you watch the video tomorrow to see this. The rest of the hour is just working on homework and asking questions.